In Chapter 6 of our course, we're going to explore normal probability distributions. Even though the textbook has 4 sections in Chapter 6, we are going to be skipping over Section 6.3, which deals with sampling distributions. Here in this first section, we're going to introduce the standard normal distribution. The standard normal distribution has 3 very specific properties. First, it is bell-shaped. We're going to see a graph of the normal distribution in a future slide, so you'll be able to see that soon. Second characteristic is that it has a mean equal to exactly 0, so the distribution is centered at 0. Third, the standard deviation is exactly 1. In this section, we develop the skill to find areas corresponding to various regions under the graph of the standard normal distribution, and we'll make the connection that those areas are going to correspond to probabilities or relative frequencies. In addition, we find z-scores that correspond to areas under the graph. This is the equation for the normal distribution. In fact, if we were to graph the normal distribution on a traditional XY plane or a traditional coordinate plane, it would meet the requirements of a function. Now, no worries, you're not going to have to deal with this equation, but it's good background to know that the graph itself can be generated by an equation that corresponds to a function. This is the graph of a normal distribution. Here we see what we are talking about when we say it is bell curved. So it looks like a bell that just has some long tails here to the left and to the right. It is symmetric, meaning that if we were to look at the mirror image of the left, it would form exactly what we see on the right. We also see that its highest peak, its highest part of the graph happens right at the center, and that these frequencies are decreasing as we move away from the center, either to the left or to the right. Note that these tails never actually reach this horizontal axis. So the horizontal axis is like an asymptote. It is a barrier that never actually is attained. Notice that in the middle of the curve, we have our mean, which is 0 in the case of the standard normal distribution. Let's talk about what a density curve is in general. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. Because the total area under any density curve is equal to 1, there's a correspondence between area and probability. I want to take a moment and pause here to make a connection to what we saw in Chapter 5. In Chapter 5, we explored probability distributions, but in all of the examples in Chapter 5, we were dealing with discrete probability distributions. Discrete because the possible values of the variable were listable. In fact, we were able to organize the probability distribution in table format. What is different here in Chapter 6 is that now we're dealing with continuous probability distributions. So those values of the random variable x are no longer listable because they're going to follow a fluid measurement scale. Now we're going to look at a type of continuous probability distribution called the uniform distributions. And the reason we do that here is that the uniform distribution has a lot of easier aspects in terms of finding areas under the curve, as you'll see in some examples that are coming up soon. So it's a way for us to practice making that connection between area and probability in an easier setting, and then applying what we learn to the more interesting normal distributions. So let's look at what a uniform distribution is. First of all, it is a continuous probability distribution. The area under the curve is equal to exactly 1. Therefore, As we said earlier, there's going to be a correspondence between area and probability. In fact, we're going to be able to find those areas under the density curve because the areas form rectangles. And the area of a rectangle is quite straightforward to calculate. It is simply height multiplied by width. A uniform distribution has its possible values of the variable x equally spread over that horizontal axis. That means that every value of x is equally likely to occur. The graph of a uniform distribution, therefore, forms a rectangular shape. Now, I want us to look at this example, which we'll use throughout the discussion here on uniform distributions. Here we're looking at wait times in minutes. So that is what our random variable x stands for. The minimum wait time is 0 minutes, and it looks like all wait times between 0 minutes and 5 minutes are equally likely to occur. I know that because the height is corresponding to the probability of x. So if every wait time between 0 minutes and 5 minutes is equally likely to occur, then the density curve forms this kind of flat line segment hovering over the values ranging from 0 to 5. Now, if the density curve then has a total area under it equal to 1, and why 1? 1 corresponds to 100%. So there is a 100% probability that the wait times will be some number between 0 and 5 minutes. Let's continue with this example. During certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed between 0 minutes and 5 minutes, as illustrated in the figure on the previous page as well as on the next page. Here is what we saw previously, and we see that all waiting times between 0 minutes and 5 minutes have an equal probability of 0.2. And I want to explain why 0.2 and why it can't be any other number than this. Again, the area of a rectangle is length times width or base times height, depending on how you label the two dimensions. But the length here of this bottom side of the rectangle is 5. 5 multiplied by what number would give us a product of 1? Well, that number is 1/5, which written in decimal form is 0.2. So the bottom part of this rectangle has a measurement of 5. The height here has a measurement of 1/5 or 0.2. 5 multiplied by 0.2 gives us exactly 1, which is the area of the rectangle, which is the area under that density curve. Waiting times can be any value between 0 minutes and 5 minutes, and any number between 0 and 5 is equally likely to occur. So possible values are real numbers between 0 and 5. For example, a waiting time of 1.234567 minutes would be possible. In fact, there's no boundary as far as how many decimal points we can go out in our precision of counting the waiting time. So it is a continuous variable. By assigning the probability of 0.2 to the height, as I mentioned earlier, we ensure that the total area under the curve, which is the area of the rectangle, equals exactly 1. In general, we should make the height of the vertical line in a uniform distribution equal to 1 divided by the range, where the range is that difference between the maximum value of x and the minimum value of x. Given the uniform distribution illustrated in the figure, here is our first question. We need to find the probability that a randomly selected passenger has a waiting time of at least 2 minutes, meaning the passenger had to wait 2 minutes or longer. If we look at what part of the density curve this corresponds to, then we really should be looking at the region where x is 2 or greater, 2 or to the right. And here it is in shaded form. So we're looking at the probability that a randomly selected passenger had to wait 2 minutes or longer, and any of those times in between would be considered. So if we find the area of this smaller rectangle, we should be able to make that connection that the area is equal to the probability. Now let's look at how to find the area. Now the base is 5 minus 2, so here the base has a measurement of 3 units. The height is still 0.2, so we have a total area of the shaded region equal to 0.6. That means that the probability of randomly selecting a passenger who has a wait time of at least 2 minutes, so 2 minutes or longer, is 0.6 or 60%. Let's return to the standard normal distribution. I mentioned earlier that the reason we talk about uniform distributions is that they make it really simple for us to make that connection between areas under the curve and probabilities. Well, this type of shape makes it a little bit harder to find areas under the curve because we don't have the flat tops to those rectangles. So we will have to use other methods to find areas under the curve. Let's revisit some of the important characteristics of the standard normal distribution. The standard normal distribution is bell-shaped. It has a mean equal to 0 and a standard deviation equal to 1. We can find areas, which are also probabilities, for different regions under a normal model using technology or using a table from our textbook labeled Table A2. It is in your formula and tables packet in Canvas, so I urge you to have a copy of Table A2 printed out and ready to refer to as you work through some practice. Technology is also available. I will show you how to calculate areas under the normal curve using your calculators in a separate video. Let's practice on how to find probabilities or areas under the standard normal curve using Table A2. Table A2 is designed only for the standard normal distribution. There's only one standard normal distribution. That's the bell-shaped curve with a mean of 0 and a standard deviation of 1. And I say this because in section 6.2, we're going to look at all sorts of normal distributions. So there's only one standard normal distribution, but there are many, many different normal distributions in general. So what makes it standard, what makes it kind of special, is that the standard normal distribution has a mean of 0 and a standard deviation of 1. Other normal distributions can have a mean that is different than 0 and or standard deviations that are some other number than 1. Table A2 falls on 2 pages of our formula packet. One page is dedicated for negative z-scores and another for positive z-scores. Each value in the body of the table represents a cumulative area from the left all the way up to a vertical boundary above a specific z-score. When working with the graph, we want to avoid confusion between z-scores and areas. So we're going to explore the table in just a bit, and I'll point out where you find z-scores and where it is that the areas are located on the table. Z-score, let's just kind of revisit that concept which we were introduced to in Chapter 3. Distance along the horizontal scale of the standard normal distribution corresponding to the number of standard deviations above or below the mean. Refer to the leftmost column and the top row of Table A2. I know that was a mouthful. We're going to practice how to find z-scores and how to relate them to areas as we explore the z-score table. The part of the z-score that denotes the second decimal place, which is the hundredths place, is found across the top of the table. Here is the first of 2 pages for table A2. This first page has negative z-scores. The next page is going to have only positive z-scores. Let's take a moment and explore what this table actually tells us. At the very top of the page, you see there is a picture of the standard normal distribution. I know it's the standard normal distribution because it is bell-shaped, it's centered at 0, and the standard deviation is 1 based on where they've located the z-score here. So the z-scores in this table fall to the left of the mean. Anything to the left of the mean is going to be a negative z-score. We're finding areas to the left of any specific z-score that is to the left of 0. So for instance, let's say that this z was equal to negative 1.36, for instance. If this z-score was negative 1.36, then I would go here to this column, go to negative 1.3, and then to capture that 6 in the second decimal place, I would scroll over to the column that had the 6 in the hundredths place. I skipped too far to the positive z-score table. Let's see if I can go back to the negative z-score table. So this first column takes you out to the first decimal place, to the tenths place, and then you scroll across the top and you find the correct hundredths place, and then where the row meets the column, that point of intersection would give you a four place decimal, and these numbers in the body of the table correspond to areas. So these areas are the areas to the left of whatever z-score you are looking up. Now let's look at the positive z-score table. If we look at the top of the page, we see that we're still looking at the total area to the left of a z-score, but now because these z-scores are positive, we're looking to the right of the mean. So any z-score that is higher than the mean is going to be positive, as we saw in chapter 3. Let's say, for instance, that this z-score at the top was equal to positive 1.72, for instance, 1.72. So we would go here to z equals 1.7 in the first column, and then to get that 2 into the hundredths place, the second decimal place, we would follow that row until we got to the 0.02 at the top for the hundredths place. And we see that that area would be equal to 0.9573. So 0.9573 would indicate the total area to the left of that z-score of 1.72. Here's a quick summary as to how to use the table. I know I kind of went through it verbally. If we're looking at the cumulative area to the left, then all we have to do is look up the z-score in table A2, and whatever 4-digit decimal is listed for that z-score, that is exactly the area to the left. If we're finding area between two z-scores, we have a little bit more work to do. What we would have to do is look up both z-scores, the one that is at the upper boundary and also at the lower boundary, and then we would take the two areas that correspond to those two z-scores and subtract them. Here it's recommending that we use technology, but I'm going to show you that it's just as easy to use the table. Let's take a look at the example that will follow us throughout the next few slides. A bone mineral density test can be helpful in identifying the presence or susceptibility of osteoporosis, a disease that causes bones to become more fragile and more likely to break. The result of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1, so these test results meet the requirements of a standard normal distribution. So in other words, the results of those bone density tests are going to follow the standard normal distribution, which has a mean of 0 and a standard deviation of exactly 1. Here is the distribution for those bone density test results. And here is the question that is being posed. A randomly selected adult undergoes a bone density test, and we want to find the probability that this person has a bone density test score less than 1.27. Well, using the table A2, if we were to look up a z-score equal to exactly positive 1.27, we would see that the area to the left would be equal to 0.8980. That means that the probability of randomly selecting a person whose density test score is less than 1.27 is 0.8980. So area is equal to probability. Here's the interpretation again. The probability that a randomly selected person has a bone density test result below 1.27 is 0.8980 because that is the four-digit decimal that corresponds to that z-score. In other words, there is an 89.8% probability that people have bone density levels below 1.27. Using the same bone density test, let's find the probability that a randomly selected person has a result above negative 1.00, which is considered to be in the normal range of bone density readings. So I want to pay attention to the wording here. This time we're looking at values that are above a given z-score, so to the right of a given z-score. Table A2 only gives us areas to the left, so if we want to find area to the right, we will have to use the complement rule. Here's how we would do that. If we look up the area to the left of the z-score equal to negative 1.00, and we subtract the table entry, which represents area, from the total area of 1, we should then have the area to the right of that z-score. Note that if the area to the left is 0.1587, then the area to the right has to be equal to 1 minus 0.1587. Again, the total area under the curve is 1, so whatever doesn't fall to the left must fall to the right. In this case, people who have bone densities greater than negative 1.00, that probability is about 84.13%. And here it is in a little bit more wording saying the same thing. Now, let's look at finding bone density test results between two values, between negative 1.00 and negative 2.50. As we said earlier, you're going to have to look up both of these z-scores in the table, and then we're going to subtract the two table entries, or subtract the two areas from one another. The area to the left of a z-score equal to negative 1.00 is 0.1587. The area to the left of z equals negative 2.50 from table A2 is 0.0062. And the area in between those two z-scores then would be found by subtracting these two areas from each other. So when you're finding area in between two z-scores, you're going to subtract the two areas from each other. Not the z-scores, but the two areas that you found from the z-scores. For this example then, it looks like there is about, let me back up a little bit, about a 15.25% chance that a randomly selected person will have a bone density result between negative 1.00 and negative 2.50. Here's a quick review of some notation that may come up as you work through your practice. In the first case here, we have the probability that a z-score will fall in between two values. The second has the probability that a z-score will be greater than some value. And in the third case, we have the probability that a z-score will be less than some specified value. Sometimes we'll have to go backwards. In the next couple of slides, we're going to be looking at how to go from known areas or known probabilities back to specific z-scores. We're going to still be using table A2 for now, but we're going to be using it in reverse. Rather than looking up a known z-score and tying that to an area, which is probability, we're going to work in reverse, and we're going to start with the known area or the probability and then find what the corresponding z-score is. And the reason we do this is because for the rest of this course, we're going to be talking about values called critical values. Critical values are nothing more than cutoff scores or thresholds. When we're talking about probability or we're talking about hypothesis testing, which we'll get to in a later chapter, we're going to be establishing these cutoff scores or these thresholds, and they're going to correspond to critical values. For the standard normal distribution, a critical value is a z-score on the borderline separating those z-scores that are significantly low or significantly high. The notation for a critical value when it comes to a z-score is the letter Z with a subscript to the bottom right. Here, this is the Greek letter alpha. It looks like a funny looking A, but it is the Greek letter alpha. So Z with alpha as a subscript corresponds to a critical value where the area to its right is equal to exactly alpha. Here's an example where we have to find a critical value. It's asking us to find the critical value where the area to the right is equal to 0.025. So that is what alpha stands for, 0.025. So let's take a look at this normal distribution in graphical form. Here we have the mean equal to 0 right at the center. We want the area to the right of Z to be equal to 0.025. Now, if we go to table A2 and we find what value comes closest in the body of the table, so we're looking at the interior of the table, we find that the closest 4-digit decimal to 0.025, if we read backwards, then that corresponds to a z-score equal to positive 1.96. Now, this table entry doesn't exactly occur in the positive z-scores, though. It occurs in the negative z-scores. So an easier way to find a critical value is to find the area that is the subscript, that's your alpha. Look at what the z-score is that corresponds to it. It will always be a negative z-score, and then basically just change the sign to positive.